Liftoff is scheduled for 10:21 and 2 seconds p.m. Pacific time. So if you are watching from the East Coast, it's going to be already early the next morning. And there's a special reason why SpaceX fuels this close to liftoff.
Yeah, and that's because they use densified propellants, which are very, very cold. And so they fuel this close because they don't want it to warm up too much, and you want to keep it down in those really cold cryogenic temperatures prior to liftoff. And SpaceX has gotten very good at that, at fueling this late in the game. They're very efficient at it, and it's just a normal part of the process at this point.
All right, so we're going to continue to keep an ear on things. Next thing we'll be listening for is the SpaceX launch conductor poll at T-minus 4 minutes. That's the next milestone you see on that progress bar on the bottom of your screen. So we'll be listening in for that. And for now, we're going to toss it back over to Daryl and Kelly.
All right, thank you very much, Marie and Denton. And now we want to get back to the science of this mission and talk a little bit about the what if, Kelly. You know, this is a big deal. A lot of people probably haven't heard of this. Like, oh, wait a second, should I be worried about, asteroids now? But it really comes down to all the documenting and cataloging that you guys are doing. So how many asteroids are out there?
Right, well, NASA-funded telescopes are responsible for most of the near-Earth asteroid discoveries, which now number 27,532, according to the Center for Near-Earth Object Studies website.
Okay, well, and that's an up-to-date number.
It is.
So what about the asteroids that we don't know about?
Well, that's the thing of the subset that are of a larger size that could really do damage that the Earth's atmosphere doesn't protect us from. That larger population, we've probably only found about 40% of those.
Only 40%, which means there's a lot more out there.
So we keep searching.
Okay, well, we keep our eyes to the skies and eventually get a telescope up there, right, to look at this.
Right. NASA funds these ground-based telescopes that search for near-Earth asteroids, and they're doing a fabulous job, but it is also developing the Near-Earth Object Surveyor mission, which will be a space-based infrared telescope really designed to do this type of survey work and accelerate the rate of discoveries of near-Earth asteroids.
Great. Space-based telescope specifically purposed for looking for asteroids.
Right.
Looking forward to that mission. And so what if there wasn't enough time, though, to knock it off course? Well, earlier, NASA's Raquel Villanueva talked to two key people about how FEMA and NASA are working together on this.
Well, there's currently no threat of an asteroid or comet heading toward Earth. There is plenty of work being done to prepare for a potential threat. I'm here today with NASA Planetary Defense Officer Lindley Johnson and Leviticus Lewis with FEMA to talk about some of the measures being taken. Leviticus, Lindley, thank you for joining us today.
Glad to be here.
Yeah, you're welcome.
Now, how do your agencies work together when it comes to planetary defense?
Well, we at NASA are tasked with trying to find any impact threat that might be out there, any asteroid or comet that is close enough to Earth that it could impact us, and then be able to determine when and where that impact might occur so that we can inform the emergency response community if we don't have enough time to do something about it in space.
FEMA is the Federal Interagency Coordinator and also an all hazards organization. So planetary defense is just one more thing on our list of hazards that we should be prepared for.
One of the many emergencies. Now, Lindley, if there were to be an asteroid that posed a threat to Earth, what is being done to discover and track this?
Well, NASA and the Planetary Defense Coordination Office sponsors projects around the country at observatories and universities, space institutes that are searching the skies every night to find any asteroid or comet that could be an impact threat to the Earth in the future. We want to find them far enough in the future that we have a chance to do something about them, like use DART to deflect them off of that impact trajectory. But if the time is short and we're not able to do that, then an asteroid impact is just like any other natural disaster, and so the emergency response community needs to know when and where and what the effects could be.
And if an asteroid poses a significant threat, what steps would be taken next?
Well, we collect as much information as we can about the asteroid through the remote observing and determining the composition and size size, it might be small enough that Earth's atmosphere would disintegrate it. But if not, then there could be damage at the surface. We want to be able to appraise the emergency response community how extensive those effects might be, what kind of area by this natural disaster.
And Leviticus, how would FEMA work with NASA if this type of scenario were to happen?
So we're not going to be changing our procedures exactly, but we want to make sure we account for the differences in the science and in this particular scenario. So there will be another emergency added to the list of things we handle every day.
Leviticus, Lindy, thank you so much for your time.
You're quite welcome.
You're welcome.
All right, DART is the first time we've ever used a spacecraft as a kinetic impactor into an asteroid. So we asked the astronauts on board the space station to demonstrate what a kinetic impact looks like in space.
Hi everyone, I'm Thomas Pesquet and I'm with my favorite astronaut Shane Kimbrough up here on the space station. Today we're going to talk about a very cool new NASA mission. It's called DART. Can you tell us and tell me a little bit more about what is NASA's DART mission?
Okay, yeah. So DART is NASA's first planetary defense test. So we're gonna try to do something we've never done before with a spacecraft. And now the purpose of this spacecraft, this mission, it has one purpose, and that's to crash itself into an asteroid and try to redirect it, try to move it into a different orbit.
So today, Shane, we're going to demonstrate some of those principles that you laid out before, but can you tell us exactly how we're going to do that?
We're going to try to demonstrate this asteroid kinetic deflection method, which is really the moment that spacecraft crashes into the asteroid. So here we go.
Shane is going to be the asteroid, and I'm going to be the NASA DART mission. I'm going to try to throw this CTB, and we'll look at the effect of that mass coming at him and the kinetic energy transfer. Shane will be perfectly stable. You ready? All right, here it comes. I've redirected Shane successfully. Pretty good. A while ago, we got out the door and we got some new solar arrays here on Space Station.
And so the same technology we have here now on the space station is going to be used to power the DART mission on its way to this asteroid.
ROSA, in case you didn't know, but you knew, it stands for ISS Rollout Solar Arrays.
So we got a chance to go outside and install the very first two of these new IROSAs, or rollout solar arrays, on the very end of the space station, out on the port side. These are different because, for one,
Ahora sí, está ajustando ahí un poco. Buenas, Ciro. Mucho venting, sí. Ya estamos a 13 minutos de lanzamiento.
Good weather forecast, and the good news right now is weather officers giving us a 0% probability of violating launch weather requirements. The ground level winds are good, the upper altitude winds are good, and we don't expect to have any weather holds for launch. The weather conditions also look good for booster landing on our drone ship and for fairing recovery in the Pacific Ocean. So with that, the launch vehicle, the spacecraft, the weather, and the range are all good to go for a 10:21 p.m. Pacific time liftoff from Space Launch Complex 4 East.
Liftoff of Falcon 9 will kick off a roughly 11-month journey for the DART payload. The DART spacecraft will separate right around 56 minutes into flight, and from there it will spend the next 11 months cruising to its intended destination, intercepting the binary asteroid system between late September and early October of 2022. DART's target asteroid is the size of 2 football fields. Impact will occur when the distance between Earth and the asteroids is near its minimum, within 6.8 million miles or 11 million kilometers of Earth. This will enable scientists to observe and measure the change in momentum of the Dimorphos asteroid. And it's worth noting that Dimorphos is not a threat to Earth. Therefore, it's a perfect testing ground to see if intentionally crashing a spacecraft into an asteroid is an effective way to change its course should an Earth-threatening asteroid be discovered in the future.
Now, the DART demonstration has been carefully designed with 4 key objectives. The first objective is to demonstrate a kinetic impact with Dimorphos, the smaller the 2 asteroids. DART will hit the asteroid nearly head-on, delivering enough energy to leave an impact crater, but not enough to destroy the asteroid, eject it from its orbit around that larger asteroid, or noticeably change the pair's orbit about the sun. Now, the second objective is to change the binary orbital period of Dimorphos. Now, the orbital period is the time it takes the smaller asteroid to circle the larger asteroid you can see here in the graphic. Currently, Dimorphos is in that original orbit. Scientists estimate the collision will shorten the smaller asteroid's orbital period by several minutes, placing it into that new blue orbit. Now, the third objective is to use ground-based telescope observations to measure the orbital period change before and after the impact. Telescopic observations in the weeks after impact will confirm that DART changed that orbital period of Dimorphos, and it'll reveal by how much. And then finally, the fourth objective is to measure the effects of the impact and the efficiency of that deflection. Now, choosing this binary asteroid target for the demonstration takes advantage of the fact that changes in that smaller asteroid's orbit around its larger partner can be more easily measured than the changes in a single asteroid's orbit around the sun.
To ensure the best possible data capture, the DART mission is taking along some pretty cool technologies to help capture this demonstration test. On board the spacecraft is the Didymos Reconnaissance and Asteroid Camera for Optical Navigation, also known as DRACO. Now, this is not to be confused with the Draco thrusters on SpaceX's Dragon spacecraft. DART's DRACO will provide real-time streaming images of the asteroid as it approaches impact. In addition to the onboard camera, the team is also flying a CubeSat from the Italian space agency known as LICIACube, which stands for Light Italian CubeSat for Imaging of Asteroids. This cube will be deployed from the DART spacecraft 10 days prior to impact with the asteroid. LICIACube will use its onboard propulsion system to alter its trajectory, offsetting so that it flies past Dimorphos approximately 3 minutes after the DART impact to capture the effects of the impact. Now, it's pretty incredible to think about what a mission like this could mean for the future of planetary defense. Now let's take a closer look at what the NASA team is hoping to achieve with the Double Asteroid Redirection Test mission.
In case there was an asteroid coming towards Earth and you're there, you can actually stop it. I mean, that's kind of fantastic.
NASA is crashing a spacecraft into an asteroid.
What? You think science fiction, but this is real. Never in my life would I have thought I would take a couple $100 million spacecraft and crash it into an asteroid. My name is Michelle Chen.
I'm Lena Adams.
My name is Kelly Fast.
I'm Andy Rifkin.
I'm Justina Sorovitz, and I help tell the story of the DART mission.
I'm a planetary defender.
And I study how the orbits of asteroids change after we hit them with spacecraft.
My job was primarily to make sure all the systems on the spacecraft work together.
The DART mission is NASA's first test of a planetary defense technique called kinetic impactor.
DART is the Double Asteroid Redirection Test.
It's just a spacecraft that is going to go and smack an asteroid.
The moonlit Dimorphos, which orbits the asteroid Didymos.
And see if we can change its trajectory just a little bit.
In order to show that we can deflect incoming asteroids if we need to.
DART will only be changing the period of the orbit of Dimorphos by a tiny amount.
But in space, just a little bit is just enough to make an asteroid actually miss us.
In the event that an asteroid is discovered well ahead of time before it might impact Earth.
Behind me, you see the spacecraft.
It's really cool to see it coming together in real life.
It is fantastic to see it in real life.
To see it turn from ideas into real pieces that are gonna go into space.
The solar arrays will actually roll out to 28 feet in length.
Once the solar arrays are deployed, it's going to be the size of a school bus. As the solar
Bueno, estamos a menos de 5 minutos para el lanzamiento.
The asteroid's only 2 football fields in size.
We're flying at over 6 kilometers a second.
30 days out, we see 1 pixel on our field of view.
You can see Didymos and Dimorphos as 1 point of light.
About 4 hours out, our spacecraft becomes autonomous.
And then that's where everything gets really exciting.
You actually are seeing impact.
We're super excited and nervous as well.
I feel really honored and humbled to be working in an area of science that has such a broader impact, you know, figuratively and literally.
No DART! The dinosaurs are made completely extinct by an asteroid impact so many years ago. Here we are, we can actually do something about it. I think this is just wonderful.
It's currently T-minus 4 minutes and counting. Everything continues to be go for launch. Spacecraft is transferred to internal power. Now on your screen, you can see the large structure next to Falcon 9. That's the strong back. Currently, the clamp arms have opened up, and you can see that the strongback has begun to retract away from the rocket. It's moving all the way back to a launch position about 77 degrees upright. Now, this is different from Falcon East Coast launches, where we move the strongback only 2 degrees, and then we retract it the rest of the way at liftoff. At Slick 4, once we get it back into position here in about another 40 seconds or so, we won't have to move it farther away at liftoff. Also, while we were watching the video, we have completed the fuel load on the first stage on time as expected, and we've begun chilling of the Merlin engines. Coming up on T-minus 3 minutes, everything continues to be go.
Stage 1 LOX load complete.
And we just heard that call out, LOX load complete. That is the first stage LOX loading being completed. Second stage will complete around T-minus 2 minutes. And Falcon 9 and DART teams continue to track no issues for launch. Weather is still looking great, as John mentioned. The range is ready to support, and SpaceX team is monitoring the completion of that second stage. Coming up next, around T-minus 2 minutes, we should hear LOX loading completing for that stage. Now, as a reminder, we do have, if we do have a hold on today's launch for any reason, we do have a backup opportunity tomorrow with a liftoff time of 10:20 p.m. Pacific time, just a minute earlier than tonight.
Coming up on T-minus 2 minutes, waiting for the call out that LOX load is in closeout.
Mandamos pantalla completa.
Those are the umbilicals that are still.
Now the SpaceX ground computers are now draining propellant out of the lines that go up the strongback to the second stage, and that creates the white cloud that you see around the strongback. Pressure from the ultra-cold liquid oxygen line is being vented, and that causes moisture in the California night air to condense. Next event will be the startup call-out at T-minus 1 minute. The first second stage computers on Falcon 9 will execute programs to prepare the rocket for flight, leading to ignition of the Merlin engines at T-minus 2 seconds and liftoff at T0.
Falcon 9's in startup.
There's that call out. Falcon 9 computers are now running the final sequence for launch. First and second stage tanks are beginning to final pressurize for launch.
Vamos.
Just waiting
Falcon 9, DART, go for launch.
And there's that final go for launch with all systems go for T0. Let's listen into the terminal count and watch Falcon 9 transport NASA's DART spacecraft into orbit.
30 segundos. 25 segundos. Ahora se me va a internet en tiempo de unos 5 segundos. No. Me callo, mando volumen al mango.
10, 9, 8,
7,
7,
6, 5,
4, 3, 2, 1,
listo.
0. Ignition. Falcon 9 with the DART mission on the way for humanity's first ever planetary defense test mission. Vehicles pitching downrange.
Debemos el Falcon 9 despegar con DART Mission.
Stage 1 chamber pressure is nominal.
30 segundos.
T plus 33 seconds. SpaceX launch engineers seeing a nominal conditions on Falcon 9 as we begin the trip to space carrying the DART spacecraft. M1D engines about to begin throttling down.
Power and telemetry nominal.
We're throttled down. Avionics calls out good power on the vehicle.
Vehicle supersonic.
Max Q, donde el vehículo sufre la mayor presión.
Max Q.
No.
We've gone supersonic. We're through the period of maximum dynamic pressure. The Merlin 1D engines have throttled back up to full power. We're out of the throttle bucket. From here on, even though the velocity is rapidly increasing, The atmospheric density is decreasing, and so the loads are decreasing now on the Falcon 9. Everything continues to look good with the stage 1 trajectory.
Invac chill has started.
Lead valve is open on the second stage engine. That's beginning the final chill prior to second stage engine ignition. Two minutes into flight, all continues to go well. In 30 seconds, we'll have 3 significant events coming up in quick succession. We'll get MECO, main engine cutoff, where we shut down the 9 Merlin engines. The stages will separate, and we'll get ignition of the MVAC-D second stage engine to power DART and the second stage into their parking orbit.
Los 2 minutos con 33 segundos, en teoría se tendría de apagar el motor de la primera etapa.
We've throttled down to hold at 4 Gs, getting ready for MECO.
En 2 minutos con 44 se enciende el motor de la segunda etapa. Bien.
MECO.
Stage separation confirmed.
Motor y separación ambas etapas. Encendete. Ahí va. Y el encendido del motor de la segunda etapa.
We've got successful stage separation. Second stage engine ignition now at full power on the Merlin engine. Next event coming up is going to be payload fairing jettison. On the left side, you can see the titanium grid fins on the first stage beginning to deploy as we get ready to bring the first stage back down to the drone ship, Of Course I Still Love You, in the Pacific Ocean. Getting ready now, there's the view of the fairing. And we've got deployment of the payload fairing, and now the DART spacecraft exposed to the vacuum of outer space. Now, we will be attempting to retrieve these new fairing halves with the help of our recovery vessel, NRC Quest.
Stage 2 on nominal trajectory.
Everything going well with Falcon 9 and DART.
What you're looking at on your screen is a live view of that MVAC engine on our second stage, burning bright. We are currently in the first of 2 planned MVAC burns for spacecraft deployment today. At T plus 6 minutes and 40 seconds, you should see on your screen, hopefully we'll get some live views of the first stage entry burn. And that entry burn will last about 30 seconds. Now, for the entry burn, we do relight the center E9 engine, and then partway through, we relight the E1 and E5 engines, so that we have 3 total M1D engines helping to slow the vehicle down as it passes back into the Earth's atmosphere. And again, what you're looking at on your screen is the MVAC engine on the second stage. We're getting some awesome live views. And everything is still looking nominal for stage 2. At T plus 5 minutes into this mission, we're just under 2 minutes away from the entry burn on the first stage, as second stage is continuing on its journey. Again, this is the first of 2 planned MVAC burns for this mission. Now, the Falcon 9 booster supporting today's mission will perform this entry burn for the 3rd time, because it's previously supported a Starlink mission earlier this year, and the
Stage 2 on nominal trajectory.
Just to call out that stage 2 is looking nominal, which is great news. The first stage booster, again, supported a Starlink mission earlier this year and the Sentinel-6A mission in November of 2020. Now, both fairing halves for this mission are brand new and will be recovered for the first time on a recovery vessel, NRC Quest. And we are just about 30 seconds away from that entry burn on first stage. as a reminder, the Merlin engines on the first stage are optimized for sea level, and these do achieve 190,000 pounds of thrust during ascent and descent. And it looks like we got a live view on your left-hand screen of the first stage.
Stage 1, FTS is safe.
Ahí está. Encendido de reentrada.
And we heard the call out as well as visual confirmation that the entry burn has begun on the first stage. Again, this is about a 30-second burn and just helps to slow the vehicle down as it's re-entering the denser part of the Earth's atmosphere.
Y ya se apagaron los 3 motores.
And as you could see, the engine shut down on your screen. We did hear a call out that entry burn is complete.
Stage 2, FTS is safe.
Stage 2 continues on a nominal trajectory.
La segunda
Now
etapa
coming
ya se
up
encuentra a
in just
23.000 kilómetros por hora.
a little over a minute will be SECO 1. That is second stage engine cutoff 1. Again, there's 2 burns for the MVAC engine on the second stage, so we are in the first burn.
Expected loss of signal code.
So
we should see this engine shut off here shortly. And about 20 seconds later, we'll see or hear the landing burn call out on first stage begin.
Invac shut down.
Órbita establecida. Ya se apagó el motor de la segunda etapa. Y en breve tendremos imágenes, me imagino, de la primera etapa con el landing burn, con el encendido de aterrizaje.
And we just
Nominal
had...
orbit insertion.
That's what we were waiting for.
Stage 1, landing burn startup.
So we got SECO 1 on second stage. We got a confirmation of good orbit, and the landing burn has begun on first stage, and now we have a live view of first stage making its way to, of course, I Still Love You.
Stage 1, landing leg deploy.
Y se nos va la señal justo en el mejor momento.
And we had some incredible views. Now we're just waiting for some confirmation of that first stage landing here in a second. As we have a live view of second stage currently with the engine cut off as it's coasting towards its targeted orbit.
Tendremos que esperar más o menos 19, 18 minutos para el encendido de la segunda etapa, el segundo encendido.
And we will wait for that confirmation of that first stage landing, but you have just witnessed Falcon 9's 26th flight for this year, and we will confirm once we have that confirmation for that first stage landing. So now at this time, our mission isn't over just yet. The second stage is now embarking on its first coast phase. Coasting in this orbit will last about 20 minutes, and we will light that MVAC engine for a second time shortly after T plus 28 minutes and 38 seconds. So we'll see you back here at T plus 28 minutes.
On the way for humanity's first ever planet. 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition. Falcon 9 with the DART mission. On the way for humanity's first ever planetary defense test mission.
Vehicle is pitching downrange. Stage 1 chamber pressure is nominal.
T plus 33 seconds. SpaceX launch engineers seeing a nominal conditions on Falcon 9 as we begin the trip to space carrying the DART spacecraft. M1D engines about to begin throttling down.
Power and telemetry nominal.
We're throttled down. Avionics calls out good power on the vehicle.
Vehicle supersonic. Max Q.
We've gone supersonic. We're through the period of maximum dynamic pressure. And the Maryland 1D engines have throttled back up to full power. We're out of the throttle bucket. From here on, even though the velocity into their parking orbit.
Cerca de la separación.
We've throttled down to hold at 4 Gs, getting ready for MECO.
MECO.
Stage separation confirmed.
Invac ignition.
We've got successful stage separation. Second stage engine ignition now at full power on the Merlin engine. Next event coming up is going to be payload fairing jettison. On the left side, you can see the titanium grid fins on the first stage beginning to deploy as we get ready to bring the first stage back down to the drone ship. Of course, I still love you in the Pacific Ocean. Getting ready now. There's the view.
Separation confirmed.
Ahí está. Vamos a pausa. Miren lo que sobra de cofia. Esta es la sonda DART. Y sobra bastante cofia.
The fairing. And we've got deployment of the payload fairing, and now the DART spacecraft exposed to the vacuum of outer space. Now we will be attempting to retrieve these new fairing halves with the help of our recovery vessel, NRC Quest.
Stage 2 on nominal trajectory.
Vamos a ver ahí el encendido de la entrada.
Stage 1, entry burn, startup.
And we heard the call out as well as visual confirmation that the entry burn has begun on the first stage. Again, this is about a 30-second burn and just helps to slow the vehicle down as it's re-entering the denser part of the Earth's atmosphere. And as you could see, the engine shut down on your screen. We did hear a call out that entry burn is complete. About 20 seconds later, we'll see or hear the landing burn call out on first stage begin.
Invac shut down.
Espera.
That's coming up in just a bit. So in the next hour, we are going to tell you everything that you ever wanted to know about asteroids and break down the DART mission from A to Z. And we're going to start with an overview of this mission.
In case there was an asteroid coming towards Earth, you're there, you can actually stop it. I mean, that's kind of fantastic.
NASA is crashing a spacecraft into an asteroid.
What? You think science fiction, but this is real.
Never in my life. 0. Ignition.
Take a couple $100 million spacecraft and crash it into an asteroid. My name is Michelle Chen.
I'm Lena Adams. My name is Kelly Fast.
I'm Andy Rifkin.
I'm Justina Sorovius, and I help tell the story of the DART mission.
I'm a planetary defender.
And I study how the orbits of asteroids change after we hit them.
My job was primarily to make sure all the systems on the spacecraft work together.
The DART mission is NASA's first test of planetary defense technique called kinetic impactor.
DART is the double asteroid redirection test.
It's just a spacecraft that is going to go and smack an asteroid.
The moonlet Dimorphos, which orbits the asteroid Didymos.
And see if we can change its trajectory just a little bit.
In order to show that we can deflect.
Stage separation confirmed.
If we need to.
DART will only be changing the period of the orbit of Dimorphos by a tiny amount. But in space, just a little bit is just enough to make an asteroid actually miss it. In the event that an asteroid is discovered well ahead of time before it might impact Earth.
Behind me, you see the spacecraft. It's really cool to see it coming together in real life.
It is fantastic to see it in real life.
To see it turn from ideas into real pieces that are going to go into space.
The solar arrays will actually roll out to 28 feet in length.
Once the solar arrays are deployed, it's going to be the size of a school bus. As the solar array opens out, it's going to swing out in this direction. The asteroid's only 2 football fields in size.
We're flying at over 6 kilometers a second.
30 days out, we see 1 pixel on our field of view.
Didymos and Dimorphos is 1 point of light.
About 4 hours out, our spacecraft becomes autonomous.
And then that's where everything gets really exciting.
You actually are seeing impact.
We're super excited and nervous as well.
I feel really honored and humbled to be working in an area of science that has such a broader impact, figuratively and literally.
The dinosaurs are made completely extinct by an asteroid impact so many years ago. Here we are. We can actually do something about it. I think this is just wonderful.
And as was mentioned in there, this is the first planetary defense mission. And this is your office we're talking about, Kelly. So for the audience out there that doesn't understand or hasn't heard of this before, what is the Planetary Defense Coordination Office? What do you do?
All right, well, NASA's actually been working on near-Earth asteroid research since 1998, so this has been going on a long time. But in 2016, it was really formalized more in the creation of this Planetary Defense Coordination Office, which is in the Planetary Science Division at NASA headquarters. And it takes that legacy near-Earth object observations program, all the, the finding them part of the program, and then combines that with these other activities like DART, like the development of the Near-Earth Object Surveyor Space Telescope, like our interagency collaborations like we saw with FEMA there, our international collaborations, and formalizing all of that and leading the Planetary Defense Coordination Office. Lindley Johnson, we say he's got the coolest title in the solar system as NASA's Planetary Defense Officer.
All right, and he sure does. I enjoy listening to him in that interview earlier. Now, throughout the show, we will be taking the most popular questions NASA gets about asteroids and posing them to experts like Kelly. This next question is for NASA expert Marina Brozovic. When was the last time an asteroid hit Earth?
Well, the answer depends on whether you're asking about small or large impacts, because Earth gets hit all the time. But luckily for us, the vast majority of these impactors are small, and they just burn in the atmosphere. The most significant fireball event in over 100 years occurred over Russia in 2014. We actually got hit by an asteroid that was the size of a small building, and that one disintegrated about 20 kilometers above the city of Chelyabinsk, and it deposited a fair number of meteorites in the ground. And I happen to have a piece of that Chelyabinsk impactor right here in my hand. But what about big impacts? The ones that leave craters tens of kilometers wide and cause a huge amount of devastation. We have to go far back in time for such an event, and those old craters are not easy to spot, because by now they're heavily eroded, they're filled with sediment, or they can be at the bottom of the ocean. But to keep the long story short, small impacts may happen all the time, especially given that about 15,000 tons of space dust hit Earth every year. And large impacts are rare, and we're talking millions of years rare. So when was the last time an asteroid hit Earth? Probably today, but the odds are it was very small and just weren't in the atmosphere.
The binary asteroid system DART is taking aim at was chosen for many reasons. Let's join Raquel Villanueva with a special guest to explain that. But first, Raquel, you saw the launch in person live. What was that like?
Ooh, it was chilly with lots of excitement and lots of cheers, lots of fun, and I am here with DART program scientist Tom Statler to talk about the asteroid mission. Like, what did you think of launch, Tom?
Oh, Raquel, it was a beautiful, beautiful launch. Tremendously exciting.
Now, can you tell me why the asteroid was chosen?
Oh, well, a binary asteroid system, and the Didymos binary asteroid system, is the perfect natural laboratory for the double asteroid redirection test. For one thing, the larger asteroid makes sure that the smaller asteroid is held in orbit around it. So there's absolutely nothing that we can do that would make this asteroid a danger to the Earth. But more important, it's about the measurement. We need to be able to measure how efficiently DART deflects the asteroid. And we're using that binary orbit of the little asteroid around the big one to do that. We're going to change the period of that orbit by just a few minutes, and we're going to be able to measure the size of that change using telescopes on Earth in the weeks and months after impact, and precisely determine exactly what it was we did.
Now, DART is called a kinetic impactor, which is intended to change the orbit of an asteroid. So what kind of mass and speed is needed to alter the orbit of this particular asteroid?
Well, the DART spacecraft weighs about 500 kilograms, which Andy Rivkin, one of the investigation team leads, said the other day is about the mass of a small cow, which is, I guess, true. And it's going to be impacting the asteroid at a speed of about 15,000 miles an hour. So at that speed, it covers the last 4 miles to impact in 1 second. Now that's going to deliver enough of a push to the asteroid to change its motion by a fraction of a millimeter per second. But it is more than just the push of the spacecraft. It's also the energy released in that tremendous collision at 15,000 miles an hour.
Now we can envision the small cap. Now, really quickly, how do you measure success for this mission?
Well, success is, of course, first we want to execute the kinetic impact and strike the asteroid. But success is really being able to see the magnitude of that change. And at the end, when the observations are done, a few months after impact, having that measurement and knowing exactly how efficiently we deflected the asteroid, and then later with additional data being able to put that in context and knowing what we might have to do for a similar asteroid or a different asteroid in the future if we ever do need to deflect.
Tom, thank you so much for answering our questions today.
My pleasure, Raquel.
I'll send it back to Daryl.
Thank you, Raquel and Tom. And so now I have a clear picture of the size: vending machine, golf cart, and cow. That's great. That's crystal clear now. Well, from time to time, you'll hear a report about an asteroid making a close approach to Earth. As my co-host Kelly Fast shows us, a simple demonstration with a basketball, an orange, and a tiny pebble can help us get a better understanding of what's a really close approach and what's not.
Well, and here we are.
Here we are, big open field.
You know, we're just talking about how sometimes you hear about asteroids that pass close to the Earth, and maybe the news will say, oh, there's an asteroid passing 10 times the distance from the Earth to the Moon. And
I think, whoa, man, that's close.
Well, yeah, it sure sounds like it, but what does that mean? And you found this basketball that looks like the Earth. And so we can do a scale model here. So if the Earth was that size, the Moon would be the size like this orange. And so what I'm going to do is I'm going to move it out to where the Moon would be if it were this size.
Oh, okay.
Here we go, probably about 25 feet, which I spaced out earlier. And so if the Earth were the size of a basketball, then the Moon would be out here. And so if an asteroid were passing like at 10 times the distance from the Earth to the Moon, you know, it would be 10 times out that way.
Right. Even probably past.
But on a cosmic scale, not that far. We still want to keep an eye on asteroids that come this close. But as asteroids pass closer to the Earth, again, they're not impacted. So we get to maybe this distance. This is about like the distance of the weather satellite. That's really starting to get close. We don't want to get that close.
What do you have to show for the asteroid?
Well, you know, if you had this type of a scale, an asteroid might be about. In fact, this is too big. This pebble is too big to represent maybe even the asteroid that took out the dinosaurs.
Really?
Yeah, really? It would probably be smaller than a grain of salt, but we wouldn't be able to see it very well here.
So is this a close?
Yeah, we would call that a close approach, but it's not an impact, and so we're good. And this seems very small relative to the Earth. But it's the speed, and they're going very fast. Like, if you've ever been at the beach, you get sandblasted when it's windy. It's the speed that's added with that can hurt. So, and that's why you get craters on surfaces when they impact. Our atmosphere does a good job of protecting us, disrupting asteroids on the way in. But if they're large enough, then they can reach the surface and do even more damage. And so that's why you don't want to find them early. Then you could do something like the DART mission, where you could deflect that asteroid just a small amount, and then it would miss the Earth as you spun the solar system into the future.
Right. Can you take us a asteroid and go out there past the moon?
Sure.
Because that just makes us feel better. Now it's way out.
Keeping where it should be out here.
I enjoyed that. That was fun.
That was a lot of fun. I can't believe you found a basketball that looked like the Earth. That was perfect.
Specifically for this demonstration. Great job, Kelly. Most scientific spacecraft have lots of instruments on board, but for DART, there's only one.
Segunda etapa. Vamos ahí. La pantalla completa. Ahí tenemos la imagen de la primera etapa aterrizada.
Welcome back to the webcast of the Falcon 9 mission carrying the DART spacecraft for NASA. And coming back with some great news, as you can see on your screen, that we didn't get a live view of touchdown. We do confirm a successful Stage 1 landing today. That is the third for this booster, the 25th landing for SpaceX this year, and SpaceX's 88th overall successful recovery of a first stage. The second stage completed its first burn, placing the Falcon 9 and the DART spacecraft.
Aquí tenemos imágenes en vivo del encendido. Ahí está. Se viene el segundo encendido. Ahí está. Se enciende el motor de la segunda etapa.
And there's that SES-2, as you can see live on your screen, lighting up there. Now this burn is planned to last a little less than 1 minute. And during that time, we will add about 3.5 kilometers per second to our velocity. Now you can see the gauge on the screen showing Stage 2 quickly gaining speed. We'll add about 3.5 kilometers per second, or about 12,500 kilometers per hour to our velocity.
Hasta los 37.000, si no me equivoco, acelera.
This burn is the second burn for this mission.
O quizás es más.
Should be coming up here shortly.
Bueno, aceleró hasta los 39.764 kilómetros por hora.
We heard that call out that MVAC has shut down. Now just waiting for confirmation of good orbit.
Nominal escape burn.
And there is that confirmation of a nominal escape burn.
Y bueno, ahora hay que esperar a tiempo más 55 para ver la separación, que es de acá dentro de 25 minutos.
Where in 10 months, the DART spacecraft and those 2 asteroids should arrive at the same time. Now, the DART spacecraft is still attached to Falcon 9's second stage.
Acá ya van a ser las 4 de la mañana.
Remaining in the launch mission, and that is spacecraft deployment. It's timed to occur at about T plus 55 minutes and 42 seconds. So we're going to take another short break, and we'll see you back here at T plus 55 minutes for the DART spacecraft deployment.
Near the southern tip of South America.
Invac ignition.
And we just got confirmation of MVAC ignition. And you can see the video there. You can see the engine coming to life.
Precise destination to impact that asteroid. So let's go over now to Megan Cruz.
Bill, thank you so much for joining us today. I know that you're a flight design expert with NASA's Launch Services Program, and you lead the team who designed DART's flight path. Can you tell me about that flight path, and was it difficult to plot out?
Unlike a lot of missions where you have a single trajectory that's going to get you to some point in Earth orbit, we're designing a new set of targets for the launch vehicle to hit on every single day, up to 90 targets in this case. So a fair bit of trajectory analysis, a lot of computer time, and a lot of work by the combined team, both here at NASA LSP and our spacecraft partners at JPL and APL, and of course, SpaceX.
Why the instantaneous window and not the longer window we typically see for scientific missions?
When we talk about launch opportunity, that is actually like the number of days that we can launch. And when we talk about launch window, that is the amount of time on a particular day that we can launch. So given the fact that we had 90 days to potentially launch this mission, and the fact that SpaceX has a pretty good history of launching on the first or second day in the opportunity, we decided that it was more efficient and better use of the limited resources that we all have to do these kinds of missions, to focus on having the best launch trajectory for each day. And if for whatever reason we weren't able to launch that day, we've got another day right behind it.
And why did you guys ultimately decide to launch from the central coast of California and not here in Florida?
Great question. Typically, for a lot of our interplanetary missions, the most important thing is to get as much energy out of the launch vehicle, and that's no different for DART. However, usually the best way to do that is to launch as close to the equator and on an easterly trajectory. So Kennedy Space Center or Cape Canaveral Space Force Station would be ideal locations for that. As it turns out, though, this particular outbound trajectory requires that outbound ground track to be more in a north-south direction. And so we're going to launch from the west coast of California and fly out on basically a southerly trajectory. And that is a much better way to launch to avoid overflight of populated land masses.
Yeah, absolutely. And where will you be, and what will you be doing during the launch?
So I'll actually be here at Kennedy Space Center. Typically, pre-COVID, in my role, I would be traveling out to the West Coast. I'll be monitoring the progress of the vehicle during ascent and making regular updates to the NASA chief engineer and right up to spacecraft separation. And then I'll be looking at the data from the rocket and making a determination of how well we did. And I'm very confident that we're going to hit that orbit very accurately.
Bill, it sounds like you'll be very busy during launch. I hope you find some time to enjoy what you guys have worked so hard to do. Thank you so much.
Thank you so much. Thank you.
All right, thank you, Megan and Bill. Planetary defense takes planetary participation. Here's a message now from Administrator Bill Nelson about NASA's leadership in this global effort.
At NASA, we are always looking upward, keeping an eye on the sky for potential hazards and exploring asteroids to help us unlock the secrets of the formation of not only our solar system, but the universe. Well, we have a new mission. NASA's Double Asteroid Redirection Test. It's known as DART. And it's going to help us learn if by intentionally crashing a spacecraft into an asteroid to see if there's any slight change in its trajectory. And this collision will change the asteroid ever so slightly, so that if you got it way away from Earth, if it was inbound to Earth, you could change that trajectory and it would escape Earth. And what DART's going to do, it's going to ram this asteroid, that is an asteroid revolving around another asteroid. It's going to ram it at 15,000 miles an hour and see if we can change that trajectory just a little bit. And DART is not going to help NASA, but indeed the world prepare in the event that an Earth-threatening asteroid were to be discovered, and we thought it was coming to Earth. So this is important. Go DART.
Thank you, Administrator Nelson. Joining us now is the Director of NASA's Science Mission Directorate's Planetary Science Division. Let's welcome Lori Glaze to the NASA hangar, who just came from the Mission Control Center. Watched the whole launch. You get to see all the cameras and the computers and everything. So first of all, I want to ask you, how was that?
It was really incredible, I have to say. Sitting there in the room with the headphones on, and you can listen to the spacecraft team as they go through all of their checks and making sure that they've got everything ready to go, and all the go for fuel, and then watching the monitors. You can see the fuel tanks filling up on both of the main booster and on the second stage, and then the final pull when you get the spacecraft teams go for launch, and then you hear the launch team say, "Is NASA ready for launch?" And NASA launch manager says, "NASA is go for launch." And then I'm going to admit that I snuck outside and watched, and it was amazing.
Clear sky. You can see it all the way.
Clear sky, lit up behind the hill there. Gorgeous.
Oh, it's so fabulous. This is so fun, Lori, because you're my boss, and I get to ask you questions. Well, and as part of your division, Planetary Defense Coordination Office is in there, and you've got the DART mission. What other missions are under the Planetary Defense portfolio?
So, great question. In addition to the DART mission, which we have just launched, we actually also have a mission. I know you've been talking about the importance of detecting and characterizing asteroids. We have a mission that's called the NEO-WISE mission, or the Near Earth Object WISE mission, which is a repurposing of the old WISE mission that we actually use to do some detection of asteroids, but also a lot of characterization so that we know what the asteroids look like, what they're made of, and what their orbits are. And then we have a new mission that we've just started developing that we're hoping to launch in the next few years. That's called the Near Earth Object Surveyor mission, or NEO Surveyor. And that mission is going to be really dedicated to looking for those near-Earth objects. That'll be its sole purpose. We're going to send it out to a stable orbit called the Lagrangian point, L1. Should be an amazing mission.
We'll have the eyes in space besides just the telescope, which is pretty neat.
Exactly.
I got to wondering, with this kinetic impactor, we're testing that. We'll find out about that in about 10 months. But do we have any other ways that we're looking at to move an asteroid off course?
Yeah, that's a great question. So there are multiple ideas that have been thought about in different techniques that have been developed and studied. The kinetic impactor is the most mature. That's why we're testing it first. But other cool ideas that are out there are things called like a gravity tractor, which would essentially adjust the mass of the object by either adding or subtracting, and then you have the changing the gravitational pull. Another idea which is out there is to potentially detonate a nuclear device, not on the, you don't want to blow up the asteroid.
Well, it sounds like Armageddon.
No, not quite. No, you don't want to do that. You want to detonate it near the asteroid to just give it a push.
How about that? Fascinating. All technologies you're working on. Lori Glaze, Director of NASA Science Mission Directorate's Planetary Science Division. Thank you for being here.
My pleasure. My pleasure.
All right, with that, it's time to ask the expert scientists at NASA another question about the asteroids. And this one, folks, this one's for NASA asteroid expert Davide Farnocchia. We're going to ask him the question, is NASA aware of any Earth-threatening asteroids?
No, there is no asteroid that we know of that is concerning in terms of a hazard. Now, We know that asteroid impacts have happened in the past and can certainly happen in the future. But we should keep in mind that those are rare events. An asteroid impact that could cause serious regional damage only happens every few thousand years or longer. Still, it's a good idea to protect us against that possibility, and the rule of the game is find asteroids before they find us. And that's why, for over 20 years, NASA has been funding search programs to observe the sky pretty much every single night to find and track asteroids. And we've been doing a pretty good job at that. So far, we've discovered more than 1 million asteroids, including 95% of the asteroids that are greater than 1 kilometer and that could come close to the Earth. Once we discover an asteroid, we project its motion into the future to assess the possibility of an impact with Earth. We have a scale called the scale that helps us rank the risk coming from each asteroid. It goes from 0, which is lowest risk, to 10, which is highest risk. The good news is that for all the asteroids that we've discovered so far, the real scale is 0, so lowest risk for the next 100 years. So, is NASA aware of any Earth-threatening asteroids? No, but we will keep searching the skies just in case.
And that's good news. We now heard about the instrument on board a little further back, the Draco camera. Now let's discuss the computer that will use Draco's camera and the images from it to autonomously fly DART into its target. Samson Rainey is back now with us from the Mission Operations Center in Maryland with a special guest to tell us more. Samson?
Hey, Daryl. Joining me right now is Smart Nav lead Michelle Chen. Michelle, give us some insights into what you call the brains of the spacecraft. How will Smart Nav allow DART to identify its target and stay on the target for the whole 4 hours before impact?
Right, so at 4 hours is when Smart Nav starts controlling the spacecraft. And if you imagine that you're the spacecraft and you're looking at the Didymos system, you're going to see the Didymos system and Didymos itself. And at about an hour to go is when the little guy Dimorphos starts eclipsing and coming out from eclipse. And it is at that point that we start guiding towards Dimorphos.
Right. So why did you choose this method for the mission as opposed to other alternatives?
So this method, we kind of need it because everyone's been talking about the 15,000 miles per hour. So that's 250 miles in 1 minute. And for us to joystick that from the ground with the 1 minute round trip flight delay for communications, it would be impossible. So we needed something autonomous on board.
That's incredible. So how are you feeling right now, and how are you going to feel, when we approach those 4 hours before impact?
Right. Yes. So APL has a lot of experience on maturing guiding technology, and SmartNav is an IRAD that we started in 8 years ago, and it's kind of like a child, right? So we've spent the past 8 years training and teaching this child to basically drive the spacecraft on its own. And like a parent would say, we're going to be sitting in the passenger seat, watching our child drive, and we're going to be really excited and nervous as all heck.
Well, we are rooting for your kid to do really well when the time comes.
Thank you.
Awesome. Thanks, Michelle. Back to you, Daryl.
All right, thank you both. And we have a fun way now, separation from the serious science, for you to participate in our mission today. And it's by signing up to be a planetary defender, just like Kelly. Here's a look at some of the people who sent us videos on how they got involved.
I'm a planetary defender. I love space, and my dog is also a planetary defender.
I am a planetary defender. Go dog.
I'm a planetary defender. Asam planetari assistant.
Jo soc defensor planetari.
Cosmo e io siamo difensori planetari. Cosmo and I are planetary defenders.
We're planetary defenders! I'm a planetary defender. Yeah!
love the kid with the rocket engines.
That was great.
Yeah. If you would like to participate in being a planetary defender, there's a website. We're going to put it up on the screen. It's at dart.jhupl.edu/planetary-defender. Again, that's dart.jhupl.edu/planetary-defender. And there's a 5-question quiz, and then if you do well, you'll receive a digital certificate so you can share it on social media or, hang it on your wall. So guess what? Daryl and Kelly took the quiz.
You did.
We have our certificate. Look at that. Oh, yeah. I am officially declared a planetary defender on NASA's double asteroid redirection test.
I am proud of you, Daryl.
Thank you, Kelly. That means a lot. So, you took the quiz, right? And you passed. And I'm glad to hear it.
That was kind of funny because I started working my way through the quiz, and I knew what the answer to the question was, but I wanted to make sure that I knew what they thought the answer to the question was, so I clicked on a hint, and a video popped up. So, and by the way, our planetary defense officer, Lindley Johnson, he also took it and he passed.
That is great to hear. That is great to hear. I was like, I need a hint. Oh, there's Nikki. What's up? All right, thank you so much. Well, we have scheduled to make it.
Acquisition of signal, HBK 26 meter. Acquisition of signal, Malindi.
Gente, se acerca el deploy.
2 second stage engine burns that have put DART on an escape trajectory from Earth. There's one more major milestone coming up to complete today's mission, and that is deployment of the DART spacecraft from the Falcon 9 second stage, due to happen in about 10 seconds from now. The view you see from the second stage camera is the DART spacecraft. We're going to listen to hear the call out and watch for DART separation.
A ver, el deploy.
DART separation confirmed.
Separación.
And to those watching, you're witnessing a successful deployment of the DART spacecraft. The impact of the DART spacecraft with the small asteroid Dimorphos is scheduled to happen sometime between the end of September and early October in 2022, when the double asteroids are closest to the Earth. Now, during impact, the spacecraft will be traveling roughly 15,000 miles per hour or 4 miles per second. This is going to be an exciting collision to witness, and we wish everyone at NASA the best of luck with the rest of the mission.
Ahora hay que esperar 11 meses para ver si la misión es exitosa. Cuando la sonda viaje 11 millones de kilómetros y se estrelle contra el asteroide.
And with successful payload deploy, that brings our webcast to a close. For continuing coverage of the NASA mission, head on over to nasa.gov/live or check them out on their social channels. Thank you to NASA for entrusting us with the DART mission, as well as the range for their support. And of course, thank you to all of our viewers. We hope that you enjoyed the webcast this evening, and we'll see you again soon.
Bueno, gente, nosotros nos estaremos reencontrando en el próximo lanzamiento, el próximo directo o en el próximo video. Así que bueno, buenas noches Latinoamérica, buen día España. Acá mismo en Uruguay son las 4.